Hey everybody. So as you can see, I am traveling again, which means that it's definitively time for another video. And then so within that and around this, I want to talk today about, again, this concept of time and geometry and the fact that to me it is very, very, very apparent at this point that the equation is kind of backwards as we've been looking at it, that uh, in my opinion, time is emergent from space as opposed to space being like a space and time being like an add-on dimension onto it. Uh, I'm not the only person overall that has this. I'm not the very first person to advance this theory, right, or create this theory. There's a lot of prominent physicists that think along these same lines. Biggest one that is most prominent and important to me overall, just because it relates mostly to what I'm doing, is Stephen Wolfram. Uh, but within that and within this overall concept, to me, like the way that I frame it overall is like kind of the bottom line is the alien analogy, right? That if we were to meet aliens tomorrow and then we show them math, I think that the aliens, their very first like reaction to it would be like, you're doing math wrong, right? And then to me it all boils down to and stems from this concept of symbols and its symbolic intelligence, and that's what has been the main question around these things for years now, for a couple thousand years at least, is intelligence inherently symbol based, like symbolic? Like, do we need the symbols, or can we advance beyond the symbol? Like, are the symbols necessary? Um, and within this, and within what I'm going to show you here, it's very apparent to me at this point that the symbols are not necessary, right? That the world is more based off of geometry and temporal geometry, very specifically within that. And the last thing that I want to say on this subject overall, before I dive like deeper and deep into this, is that like for me very specific. So I run a business overall, right? That's my number one thing, and as a human, like my that lives on Earth in 2025, my I need to eat, right? And then so within that, like everything revolves around money and generation of money within that. And then th- these arguments and this position is like counter to me eating. Like is the bottom line, right? Because uh, this is like so essentially within this, I am trying and having to convince you that there is a problem that you don't know exists yet, and then go from there, right? Uh, there's nothing to sell you within that, right? Like step one, I have to prove that this problem exists. Like there's nothing monetizable within that. Like I would far much rather have all of this not be true. Like that's the most simplistic way that I can put this and frame this, right? Like if in my perfect world, the universe wouldn't operate this way. I am just going based off of uh, where all of my experiments lead me towards in these instances, and then just doing and looking at the same data as everyone else, right? And then drawing conclusions from there. And then the conclusions that I draw from there are unfortunate for my business needs. And then, but so here we are, and let's dive into it. So, when we imagine a computer, we usually picture a machine that counts. It deals in ones and zeros in discrete steps and rigid rules. Step one, do this. Step two, do that. In the traditional view, time is just a clock ticking in the background, measuring how fast the computer works. That's the important part of it. Like in the traditional view, like time is not built into computation whatsoever, right? Like there's the computer doesn't experience time. There's no rules related to time. You have to write rules around time. But two recent experiments, the ones that I'm going to show you in AI, suggest that we have this backwards. What if the steps aren't fundamental? What if time, the continuous flowing geometric time, is the foundation of everything, and logic is just what happens when that flow settles down, like taking the snapshot, like a camera, and then just taking a specific snapshot of that moment. This is the story of geometric computing, a new approach that suggests that intelligence isn't about processing symbols, it's about understanding the shape of the flow. In the first experiment that I'll show you, the computer that felt the answer. In the first experiment, researchers tried to teach an AI to act like a computer, to do math and make logical decisions without ever teaching it the rules of arithmetic or logic. Instead of digital switches, they simulated a torus, a donut shape. So imagine a ring where numbers aren't written down but are represented by angles. To multiply numbers, you rotate the ring. That's why I have that image. That's the best way that I look at this is like a safe, like safe cracking, or the other way that I look at this is my analogy in my head is a key and a lock, right? And then the best way that I think of and I frame that key and the lock analogy is that everyone thinks that like the key is the real shape, right? That the key is real, like the end result, but the key is emergent from the lock, right? And from the geometry of the lock, like and whatever that like the shape of the lock is, that determines what that key will be in order to open it. And that's the same way that I am looking at and treating data in this instance when it comes to time, and then very specifically this is more important when it comes to the second experiment, but I'm just mentioning it and highlighting it now, right? And then to make decisions within this, you create valleys on the ring. So like if you drop a ball, it will naturally roll into the true valley or the false valley. And then so you can think of it kind of that way, like the metaphor that I've used before with like the latent space, and imagine that your base latent space is just a flat surface. And then you want to change the dynamics of that latent space, so then you create two basins within that latent space, right? You create a true basin and a false basin, and then you're just hammering rain into the latent space world in order to create those basins. And then so you hammer enough rain into that latent space world, create these two basins, and then you throw more rain into the world. You see which basin does it fall into from there, and that's essentially how it works, right? And then so in this instance, the AI watched these spinning rings and rolling balls. It never saw a 1 or a 0. It never saw an if-then command. It only saw the continuous movement of angles. The result? The AI learned to compute perfectly. It learned that logic isn't a rule written in a book. It's a physical shape, a basin of attraction that guides the flow of information. It proved that you don't need symbols to think. You just need the right geometry. And then within this, like to me, these are like hard subjects overall, because they cross several boundaries of like physics, philosophy, etc. Right? And then so within these experiments, I proved that this is true with regards towards computation, and with regards towards all of the physics with regards towards computation. Is that true in like the real world? That would be like the next step of that experiment and the next extent of that experiment, right? So experiment 2 is zooming out on time, and then the second experiment tackled a different problem: noise. Imagine trying to predict the stock market or the weather. If you look at the data second by second, it looks like jagged, random chaos. Traditional AI gets confused by this, we'll call it jitter. It tries to predict the next random spike. To solve this, we built a temporal geometry network. Instead of looking at the last second, the AI uses a technique called dilation to look at time differently. Think of it like a pointless painting. If you stand 1 inch away, you see chaotic dots. If you step back 10 feet, you see a clear picture. And then that's what the AI did. And so this particular um, temporal geometry network is broken up and made up of different layers, right? And then so every single layer only looks at the past. And then so layer 1 looks at the last minute, layer 2 looks at the last hour, layer 3 looks at the last day. And then you're stacking those layers within it, right? And then so that's the big breakthrough within this, right? And then so like traditional recurrent neural networks, etc. They operate under the understanding of physics with regards towards general relativity, right? That you like time is an extra dimension that you add on. So they're always looking like 1 second back, and then my argument is that time is the structural element, and that there's like geometry to that time and that structure, and then we can examine that geometry of that structure if we look back more than just 1 second, and then also too if we layer that looking back, right? So layer 1 is looking back 1 minute, layer 2 is looking back 1 hour, layer 3 is looking back 1 day, layer 4 would look back 1 week, layer 5 1 month, layer 6 1 year, layer 7 1 decade, etc., right? And then that gives you those layers, and it's the process of looking back in those individual sequences, but then also layering that looking back, right? Having it layer 1 through 8 that you're going through, that all of that combined is where you get the pattern, right? So the result is, by zooming out exponentially, the AI learned to ignore the chaotic noise entirely, discovered the smooth hidden wave moving beneath the static. It learned that reality has a shape over time, and if you can see that shape, then the chaos disappears and just like completely melts off. And that's what I'll show you within that, right? And then so the big idea is the whirlpool theory. So what connects these two experiments? It's a radical idea that challenges how we understand physics. Usually we think of the universe as a collection of things, atoms, planets, rigid objects that move through time. We think that the things are real and time is just a measurement. These experiments suggest the opposite. They suggest that time is the real thing and the things are just stable patterns in the flow, snapshots of time. And so think of a whirlpool in a river. Does the whirlpool exist as a solid object? No, then you can't pick it up. The whirlpool is emergent. It exists only because the water is flowing in a specific way. If the flow stops, then the structure vanishes. The torus computer suggests that logic is just a whirlpool, a stable pattern in the flow of information. And the temporal network suggests that the truth is visible only when you look at the flow over long periods and not single moments. So why does this all matter, and why is it scary to me specifically? So this implies that we don't need to teach AI rules about the world. We need to build AI that can perceive the geometry of time. The implications are profound and perhaps unsettling. If spatial structure, the donut, the valley, the logic gate, emerges from temporal dynamics, the flow, the rotation, the update, then time is not a bolt-on dimension at all. Time is the ultimate architect. This doesn't necessarily break physics, it deepens it. It aligns with modern theories in quantum gravity that suggest that space itself is stitched together by the entanglement of events in time. We're moving from an era of digital computing involving stacking blocks to fluid computing, more like shaping water. And the machines that we're building aren't just calculating the future, they're learning to flow with it. And so with that said, let me show you the two models here and the two experiments. And then the first one that I'll showcase here for you is the geometric torus computer. And if you want to dive deep into exactly what this is doing on every single level, you can look through the top here. But just giving you the overall gist of this, it's broken up into two parts, right? And then so part one is a experiment utilizing Kiramoto geometry and Kiramoto steps, and then so the model is trained 100% purely on Kiramoto steps, which are like that geometry base and that true false base and that experiment that I laid out at the top, where it's essentially raining true false, right? And then we do that and essentially like train the latent space and the model based off of that, and then so it's trying to determine true false statements, and then within this it's able to determine within 100% accuracy, train it for like a little over 2 minutes on CPU, and then so it would be like seconds on a GPU of training in order to get this, and then so it's very quick, very fast results within this very little training overall, right? And then the second part within this, like the main part, is the full torus logic computer, or the TLC learner. And then you can adjust these up and down, right? And then so adjusting these up and down will significantly increase the performance within this. I set the performance of this like rather low in order to train it fully in time, right? And like in order to like it still took like 15 minutes on a GPU of full training within this. But the big thing that I want to point out within this is the loss rate. Like the loss was insane, right? Like so the model 100% learns and adapts to this. Like I've never seen a model have a loss rate this low. And then every single loss rate that I've ever seen trained on a model utilizes like arithmetic and or spatial geometry. And then in this instance, this is the very first time where I've trained like a model like fully on temporal geometry as opposed to spatial geometry. And look at that loss rate, right? And then so like that's like when I make the argument that if we were to meet aliens tomorrow, they would say, "Hey, you guys are doing math wrong because of this," right? Like, because like if an alien were to do math, I'm assuming that they wouldn't use symbols. And then so their very first, like we would say, "Hey, aliens, we haven't been able to figure out like if intelligence is symbol based or not. Like if you actually need the symbols." And they would just like laugh and they'd say, like, "Of course you don't need the symbols. Like the symbols are emergent from time." It's essentially like what they would say within that, right? And they would draw that conclusion just because it's easier overall. It solves more things if you actually do this and actually work within this, right? And then so within that, essentially, I train this method here. And this geometric torus computer is a complete reconstruction of a method created by Ash Kelly. So I want to highlight that and point that out here. But in this instance, I utilize it, and I on my recreation and small memory basis within this, and we can see we get more passes than failures within this. And then the failures aren't very like they're very minor when you're looking at this, and where the failures are within this is like some of them are super minor, right? But essentially what it's doing is like, so you have like, you know, base 2, 3, 4, 5, 7, 11 up to 29, and then the model is just essentially like trying to tune and guess like the next sequence within in that base sequence pattern, but it's never been trained on like actual geometry in any way, right? Or actual like symbol usage in any way whatsoever. And then so we can see, as you can see, the loss rate was phenomenal on that. And then here's all of the test results. So like this is essentially the first model trained to utilize and do like computational functions, so like 0-1 functions, 0-1 style functions, but without the symbols, without the zeros and the ones, right? 0, 1, 0, 0, 1, etc. Those are symbols. And this is more just like those attractor basins, right? Gravity, and which basin does the ball fall into, or the marble fall into, and that's like literally all it's using for its computation and logic, and it's able to perform like a computer and able to do computation and logic just purely based off of that, no symbols. So again, it's able to compute without symbols. So that proves that computation is possible without symbolic reasoning overall. And then tying it very specifically into temporal geometry, I have here the experiment of the temporal geometry network, and so here you can again look at the top here for the very deep dive into the experiment here. But so what I want to highlight, the main thing I want to highlight within this and talk about within this one is this graph, right? And then so the main things to pay attention to are that the green dotted lines are the actual structure, the geometry that exists within the data set as it relates to time series in this instance. And then the red is the model predicting in that. And then the gray dots are a bunch of noise that I throw into the data. So essentially, within this experiment is what I laid out at the top, right? Where the model is looking back at time, different layers, and so this model can only look backwards, right? It can look backwards like 1 second, 1 minute, 1 hour, etc., right? And then think of this data as like stock market data, anything that's time series, right? This you would typically utilize an RNN for this, and then RNNs struggle when you have noise in the data like this, right? Like the biggest problem with RNNs is dealing with and cutting through this noise. Like in if you have a 100% perfect data set, an RNN will perform flawlessly. But when you inject noise into it, the RNN struggles, and the RNN is always looking 1 second back, right? That's the inherent way that architecture works. And then so the big difference is, again, looking 1 second plus 1 minute plus 1 hour plus 1 day, and then also layering those, like the layering process itself, like layer 1 through 8, and then that interaction. And then to me, both of those things are significant within this. And then what you're seeing is in this instance, this model overcoming that huge problem that typical RNN models face when it comes to this type of data, and overcoming the noise in the data, right? And then so very specifically, I take that time series data, and then again just like inject a bunch of random noise into the data, and the model just cuts right through that noise. It's like, yeah, this is noise, and then this is the actual shape, and then all it's again not trained on any sort of symbol usage, etc. All it's doing within this instance is tracing and looking for that temporal geometry, the geometry that exists within the time series data itself, and then utilizing the geometry of time in order to map and make predictions in this instance. And then so if that underlying geometry didn't exist, weren't there, the model wouldn't be able to predict off of it. And then so here we are, the model's making predictions, making very accurate predictions off of something that has to exist there, or else it wouldn't make these very accurate predictions. And then so I'll leave it up to there and all of that within this, and leave it there overall within this, right? And then so I'll leave a link to the Substack notebook here, which has a link to everything that I went over here. And if you like this type of content, please like and subscribe. Thank you very much.